Hello students. In this video, I will discuss the techniques of graphing or sketching the graph of some functions, and I will try to take some examples in which I can cover the different concepts that we need to take care when graphing a function. Okay, let me begin. I will begin with number 24. So what we have here is a polynomial function. Okay. So when graphing or when sketching the graph of a function, we always want to know few things like domain. We need to know in which from on what values of x-axis is the function defined, right? In this case, the domain will be minus infinity to infinity because it's a polynomial. Some information, as you can gather, and then you would want to know if there are any asymptotes. Okay, there is no particular order in which you have to do. I just to think of whatever comes to my mind, and for different functions you can do it in different order. Okay, for example, in this case I'm talking about asymptotes first because I know it's a polynomial and it doesn't have asymptotes. Okay, so we can rule them out. So there are two types again, right? Vertical asymptote and you have horizontal asymptotes. Now, to have a vertical asymptote, the function should go to infinity at a finite point. That's important. Okay, the values of the function should become infinity or minus infinity at a finite point in a continuous way. Then it becomes, then you have a vertical asymptote. So in this case, the answer is none. They don't have it. It doesn't have any. And horizontal asymptote, you get horizontal asymptote in two situations only. Okay, x goes to infinity and x goes to negative infinity, because horizontal asymptote is the behavior of the function in the long term, not at any finite value. Now that is, and you might get some finite constant value as a horizontal asymptote if the function is like a rational function in which um, the quotient is constant but the denominator is dominating, so the denominator ultimately the fraction goes to zero, or some exponential functions which tend to be asymptotic to x-axis and things like that. Okay, now in a polynomial, again, that never happens unless it is a constant polynomial, in which case it is its own asymptote. So none. Okay, so we didn't have vertical asymptote, we didn't have horizontal asymptote. So when you discuss about horizontal asymptote, an offshoot from that is you can also think immediately from the perspective of end behavior. So we are saying there are no horizontal asymptotes, but then what is happening at the end? As x goes to infinity and as x goes to negative infinity. Now, this is a college algebra topic. Depends on the exponent of the leading term, right? This has an even degree. Okay, and the coefficient here, the coefficient of x is 1 here. It's 1x to the 4, which is positive greater than 0. So two things, the leading exponent is even and its coefficient is greater than 0. That means I will write that here now. The end behavior will be this. It'll go to infinity, plus infinity on both sides. Okay. If the exponent is odd, it goes to infinity on one side and minus infinity on the other side, right? And which side goes to which depends on the coefficient. When the coefficient is positive and the exponent is even, both infinity, otherwise both minus infinity. I hope you can see that quite easily. So I'll move on. Okay, so some things I could immediately discuss, and then there are other things, right? Now let's move on to more substantial things like intercepts. which we will need in any function. Okay, for any functions you want to know the intercepts. Again, two types, right? The x-intercepts and the uh, y-intercepts. Okay, now let me write the y-intercept. Because for any function, there is only one y-intercept, if it is a function. So that is when you plug in x equal to 0, what you get? 0, 1. That's your y-intercept. X-intercepts are the zeros of the function. Now that is a degree 4, right? Okay. Let me write this concept first here. X-intercepts are zeros. Okay. So let us look at this polynomial. I will discuss that for a second. What kind of zeros does it have? The first thing is, if you look at a polynomial, you look at the constant term. This comes from the factor theorem and remainder theorem, right? If you have a constant term 1 there, its factors are +1 or -1 only, and those can be the only rational zeros. Okay, so first we try to find the rational zeros if possible. And actually it depends on whether the coefficient is leading coefficient is 1 or not. Okay, when the leading coefficient is 1, this is particularly simple. Okay, so you only have to consider two situations, plus and -1. So you ask the question, are they zeros of this polynomial? Okay, so that means when you substitute them, does it become 0? And obvious answer is no. Okay, because there is a coefficient 270, you can see there, so like you don't have to like even give a second thought. So both of these are not going to be zeros of the polynomial. And then that means this implication is no rational zeros. Okay, so now I'm not saying there are no zeros. See, we have to be careful here, right? We are not saying there are no zeros, no real zeros. There could be some other real zeros, but they are not going to be rational numbers. All right. So which means I'm going to abandon an attempt to try and find the zeros, try and find the x-intercepts analytically. Okay. I don't know if any other technique comes up later. Analytically, we'll give up that. So question is then how many zeros? Okay, now the next question is this. Let me write that down here. Related to this x-intercepts, how many? We might want to know that and know an answer to that question, right? And because x1 and -1 are not zeros, at this point we don't know. Okay. And if you are thinking about 4, that is the maximum possible number of zeros. Okay. And I can give you quickly two situations. For example, I'm not saying that is the sketch of this function. I'm talking about any general quadratic, biquadratic function with degree 4. Okay. So you can have a graph go like that and does not have any zeros. You can have a graph go like that and have 2 zeros. Or you can have it go like that and touch it here, so only 1 0. So basically everything is possible. You may have 0 number of zeros, 1 number of zeros, 2 number of zeros, 3 number of zeros, 4 number of zeros, right? That is the range of values for a what you call polynomial like this here. And because of this end behavior, both going to infinity, at this point we cannot say anything other than saying that there are not going to be any rational numbers in the zeros, list of zeros. Okay, so we'll try to graph the function with some other things. Okay, finally, let's start the calculus, right? We have been analyzing everything else. Okay, that is where you start with the derivative. let's see what do the derivatives tell us about the function. See, so at this point, I will pause and I'll tell this is the approach. First, basically our approach should be maximum extraction of information at any phase. So even before I wrote the first derivative, I was trying to see what I can gather about the function. Okay. And then once you find the first derivative, try to see what you can gather about the function. And sometimes you might immediately want to use the second derivative even for that, because to find the max or min, you can use the second derivative test. But the point is, once you find the first derivative and second derivative, again, we'll try to see as much information as you can squeeze out of them. Okay. Now let's find the derivatives. 4x cube plus 24x squared minus 540x. Okay. Now this function had a missing x term, so there is no constant in the derivative, which is good news. Now you can you see that you can set it equal to 0 and solve it in rather easy fashion. Let me go ahead and write the second derivative also, because it will be useful. Okay. Actually, I don't know if we can drag this down. Let me erase it. Sorry about that. Let me factor the first derivative a little bit. Okay, it will be useful later. So that will be, because I can see that 4 is a common factor and x is a common factor, x square plus 6x minus 135. Okay, that will be the factoring there. Let me write the second derivative in a different color. Will be 12x squared plus 48x minus 540. And let us see if we can factor it. I can say 12x will be a factor, 12, not 12x, sorry. 12 will be a factor here. I can say that because earlier we took 4 as a factor from 540 and what remained is 135. 1 plus 3 plus 5 is 9. Okay. If the sum of digits is divisible by 3, then the number is divisible by 3. Fun fact. Okay. So 4 times 3, 12 should be a factor there. X square plus 4x minus, let me divide 135 by 3, which is 45, rather easy. So you can see that is the factoring. Okay, so we have first derivative and second derivative and we have them factored. Okay, so from the first derivative, we know the usual stuff, right? We get the critical numbers. The two types, right? One type where the derivative does not exist. And in this case, I will say f prime f exists for all x. Okay, so there's no point looking further in that. I will try to see if I can get anything by setting the derivative to 0. That is the second type. And that's rather easy because you can see that will lead you to 4x times, factor it, two numbers whose difference is 6 and product is 135. Now, multiple of numbers is a useful thing to know here. Okay. 135 is a multiple of 15. 15 times 10 is 150 minus 1 if you do, instead of 10, if you multiply by 9, it should be 15 less, 135. So then it's easy to see 15 times 9. So 9 and 15, the difference is 6. Okay. Now, if that doesn't come to your mind immediately, catch the fact that the difference is 6. So try, let's say 1 and 7. Difference is 6, right? But 7 times 1 doesn't work. Then try 2 and 8. obviously doesn't work. 3 and 9, 4 and 10. You keep trying like that until you reach 9 and 15, which works. Okay, that is another way to figure it out. All right, so 9 and 15 plus 6, so I'm going to write plus 15 here and minus 9 here, equal to 0. So that gives you x as 0, 9 and minus 15, right? Okay, and those are the critical numbers. And are they max or min? We know the number line. Second derivative test, I can do that on the number line. Okay, and actually let me draw a single number line in which I will do everything. Okay, first derivative, second derivative, sorry, second derivative test, and also later we'll use it for inflection points. Minus 15 is here. Let me give enough gap so I can use other things later. 0 is here, 9 is here. Okay, and I want to know whether these are max or min, and let me use the second derivative for that, right? If you compute f double prime at each of these, okay, at minus 15, what is the second derivative? Minus 15 square will be 225, and immediately I see it's going to be positive because you see here, this is the factor. X square plus 4x minus 45 is the second derivative. Now, if you plug in minus 15, you get minus 15 whole squared, which is 225. So that's concave up there. Okay. So, which means this is a point of minimum. Then at 0, obviously it is negative, concave down. So that's a point of maximum, local minimum, local maximum. Okay. Don't forget, these are all local. And then at 9, 9 square is 81 plus 4 times 9 is going to be more, so definitely positive. So again, concave up and local min. Okay. So we know where the function has max and local mean, right? Now, later on, I will erase this, and when I draw the x-axis and y-axis, I know the peaks and downs. Okay. What else we will have to know is the inflection points. The inflection points definitely now are going to be between this, between minus 15 and 0. I'm going to definitely have an inflection point, right? Then between 0 and 9, I'll have another inflection point. But to get that, what I need to do, I need to set the second derivative to 0. Okay. Set the second derivative to 0. I want to find space to write that. I'm going to write on the corner here. Inflection points. Okay, second derivative equal to 0. And that gives you, factor it. Again, product is 45, difference is 4. I guess you can see easily that's x plus 9 and x minus 5, right? So your values are minus 9 and 5. Okay. And luckily, our second derivative test already happened here, because you wanted, what do we do? After we find the points where the second derivative is 0, sorry, not the second derivative test, the inflection test. After we find the points where the second derivative is 0, which is minus 9 and 5 in this case, we are supposed to take 1 point in each interval, right? 1 to the left of minus 9, 1 between minus 9 and 5, and 1 to the right side of 5. And check for the second derivative, is this concave up or concave down? So we will know whether those values, minus 9 and 5, are inflection points or not. Now, we had already done that for the first derivative test. No, not the first derivative test. To find the max or mean using the second derivative test, we had already determined the concave up and concave down there. So which tells us that both minus 9 and 5 are inflection points. Okay, both yes, yes, both are inflection. But if you look at the number line. Okay, I think we have as much information as possible on this screen here that we can use to sketch the graph. One thing that is required now is this. Okay, think about this. So you can imagine it's coming from infinity on the left side because of the end behavior, and then it has a minimum at minus 15, then it goes up, that whole part is concave up. Then by the time it reaches 0, it is concave down. So at minus 9, the second derivative is 0, it's almost flat, almost like a straight line. Second derivative equal to 0 means no curvature. That means the graph should be like a straight line at that point. Okay, at minus 9, it will be almost like a straight line. Then it goes concave down. At 0, it reaches the local max, and again concave down, coming down. And at 5, again straight line, almost like a straight line, so another inflection point. And after 5, it is concave up again, right? And it turns around at 9, where there is a local minimum. So I know the shape. What I need to know is, does this happen, does any of this happen below the x-axis? Okay, especially the question is those local minimums and local maximum, we need to know their values. Okay, to get a most approximate, most accurate sketch, all that we need to do now is at each of the local min and local max, we need to compute the value of the function. That will tell us, exactly on the grid where the graph is located. And depending on where those mins and max are, I'm guessing we'll have all 4 zeros in this case. Will not know their values, as I mentioned earlier, because these are going to be only some real numbers, not rational numbers. But we will know it has either 1 0 or 2 0 or 3 0 or 4 zeros or no zero. Okay, that is the task left, computing local means and local max. Then we are ready to graph this function. I'm going to now delete what is on the screen and then compute those local min, local max, and graph it. Okay. Let me delete all of this. Okay, so the values of the functions at these 3 points, right? We had determined minus 15, 0, and 9. This is x values, and we need to compute f of x values. Okay, now I'm just not going to literally do them here. Okay, I will just talk about the approximate values. I see minus 270 x square. This is a big term. Okay, this is going to make things negative. So I'm assuming it's going to be negative. Let me try. Okay, if I take x square as a common factor, I get x square plus 8x minus 270. Then there is plus 1. I'm not factoring it. I'm just trying to see whether the values will be positive or negative at minus 15. Now at minus 15, this will be 225. This will be 8 times 15. is how much? 150 minus 30, 120. Okay, that's positive. Overall, it's going to be 225 plus 120 minus 270, which is not able to make it negative. Okay, so this value is something positive. It's above the x-axis. I mean, it's the positive is not increasing or decreasing or inflection here. Above x-axis. Okay, and similarly, if you plug in 0, clearly 0 1 that we already did, actually that's the y-intercept, and then that is again positive. Something is wrong here. Did I miss any information? 225. Oh, x is minus 15. I'm sorry. Okay, I made a mistake here. Because I was thinking, how can it be, positive at minus 15 and again positive at 0, but only 1, then it has to be between 0 and 1 at minus 15. That sounded illogical. I made a mistake here. It's minus 120 here. X is minus 15, right? You might have caught that if you are watching the video carefully. Okay, so this is negative. My bad. Let me correct this here. So this value was negative. So I can see that this function is going to have all 4 zeros. I can almost see that. Okay, we will, of course, justify it more carefully in a second. Now here is going to be negative. Okay, so below x-axis. Minus 120 minus 270, will make it much more negative than 225. At 0, it is 1. And similarly, when you plug in 9, okay, when you plug in 9, you are only going to, you are still going to be negative, because let me see. If I plug in 9, that's 81 and that's 72, but still you have minus 270, right? So overall, it will be negative. Okay. All right. I think I need to graph this and be done. This is my x-axis and y-axis. Let's say minus 15 is here. 0 1 is our y-intercept. And let's say 9 is here. I should have done more to the left anyway. Let me now sketch it. So it's going to, end behavior is up there like that, right? Here it's going up and it is again come down here and go up. What we need to mark here is the inflection values. At minus 9, okay, it's almost like a straight line. And at 5 again, almost like a straight line. That will be the graph of the function. So about the zeros, finally, we do not know what the zeros are, but we know the approximate values now, right? Or at least the ranges. There is 1 0 which is less than minus 15. There is a 0 between minus 9 and 0. There is another 0 which is between 0 and 5. And the other 0 is greater than 9. So we know the size, of the zeros of the polynomial, even though we do not know their values. And that is the graph. Okay. In this video, let me see. I'm going to erase this now. Let me see if some concepts I can discuss. Okay. Regarding number 25, one thing I will say is I'm not going to do it in detail. Just the end behavior part. It's cube there, right? So it's going to go to infinity on one side, then minus infinity on the negative side. As a result, you will have at least 1 0. Okay. And what is that 1 0? In this case, if you want to find the 0 in an analytic way, there is a lot of work to do. You have to look at factors of 140. So there are 1, 2, luckily 3 doesn't divide, but 5 will divide, 7 will divide, then 10 will divide, 14 will divide, obviously, and I think 28, yeah, 28 will divide, and nothing after that, I guess. I don't know. I might have missed something, but anyway, we don't have to try all of them. If you test with all of them, you might find a 0 if there is one. And then you can factor the remaining quadratic part after doing the synthetic division. Okay. So you will be able to know the zeros. The rest of the process is similar. Okay. Let me discuss. I'm trying to do varieties here. Let me discuss number 27 next. Okay. I think in this video it will not be possible. So I'll just talk about some ideas. And then in the next video, I will graph number 27 and possibly some more. Okay. If you want to think, I'll give you the idea. The idea is in number 27, the domain is not minus infinity to infinity. Okay. There is an under root function. So your domain is restricted from 0 to infinity. First thing. Second thing, the 0 is included. It will be square 0 to infinity. But by the time you find the derivative, that root x will go to denominator, and then you cannot even have 0. Okay. So I can see already 0 will be a critical number, but it will, because it's in the domain, it will be a critical number where the first derivative does not exist. That type of critical number. Okay. And because it's the end point where the graph begins, and it's not a constant function, obviously, which means that point is either a minimum or maximum for sure. Okay. The 0. Local mean or local maximum, it is going to be guaranteed, one of them. If it is increasing at that point, it will be a local minimum. If it is decreasing right at 0, then it will be a local maximum. And then we will find some other local means or local max, right? And you can again say there is no asymptote because there is x, you know. Um, it's a polynomial, again, the no horizontal asymptote, no denominator, so no vertical asymptote either. Some things we can gather already, right? And then can go on. Okay, I think I can talk more about that in the next video. In number 29, which I do probably after that, you see there is denominator here. Now you will get vertical asymptotes. Okay. And let me, in the same spirit, let me talk about some other situations. Okay. I don't know if I will do all of them or not. So let me give the ideas here. In number 34, you will not get vertical asymptotes, even though there is a denominator. Okay. It's not like, oh, okay, something happened with Pearson and they signed me out. Anyway, it was time to stop the video. I will discuss more in the next video. Okay, see you.